Hello and welcome back to HK Academy channel. Most engineers assume that if a boost converter looks stable in an averaged model, it will behave the same in real hardware. But that's not always true. In fact, the moment you include switching effects, you often get larger voltage deviations, slower response, and sometimes even instability. So the question is, can you really trust your averaged model? In this video, I will show you a complete closed-loop boost converter design using a Type 3 compensator. We will start with the averaged model, where everything looks clean and predictable, and then move to the full switching simulation to see what actually changes. And more importantly, I will show you how to interpret those differences like an engineer, not just what changes, but why it changes. First, I will show you the averaged closed-loop model of the boost converter, and then we will switch to the full switching model so you can see how closely the behavior matches. Before we look at the control loop, here is a quick overview of the model. Although the real circuit uses a MOSFET and a diode, in this simulation they are replaced with an averaged model. The switching action is mathematically averaged into a continuous duty cycle input, so this model captures only the low frequency dynamics of the converter. This allows us to analyze the control loop without switching ripple and significantly speeds up simulation. The power stage still includes all important non-idealities, the inductor DCR and the output capacitor and the output capacitor ESR, and as well the load resistance. In this example, the converter steps up 12 volt on the input to 24 volts on the output with a design based on a 200 kilohertz switching frequency. Now let's look at the control structure. We have a standard voltage feedback network. R1 and R4 form the output voltage divider, but R1 also plays a role inside the compensator, forming the integrator together with the capacitor C1. The lower resistor R4 only defines the scaling and is not part of the compensator dynamics. Here is the full Type 3 compensator. It provides two zeros for phase boost, two high frequency poles for noise attenuation, and an integrator for zero steady state error. This compensator is designed for a crossover frequency of about 1.5 kHz and a phase margin close to 70 degrees. Let's now run the transient simulation. Duration of this simulation is 12 milliseconds. We will observe the output voltage, and then we will observe as well the load current. Here I apply a load step of 50 milliamps, and we will observe the output voltage. Now the simulation takes some time, and we will wait until the simulation is finished. But here you can see also during the startup that we have the ramp for our voltage, and we have just a small overshoot. Here you can observe at 7 millisecond we apply the load step of 50 milliamps. You can observe here, and then after 2 milliseconds, exactly at 9 milliseconds, we disconnect the load, and in that case we only have 50 milliamps instead of 100 milliamps. Okay, now we can zoom and see what is happening with our output voltage during the load step. And here we will just auto range epsilon axis, and now we can observe. Now you can clearly see a transient response. There is a small voltage dip when the load increases, followed by a controlled recovery, and a slight overshoot when the load is removed. The total deviation is around 200 millivolts, and the system settles roughly in about 1 millisecond approximately. And this is important. Even though this is an averaged model, the response is not perfect. We still see overshoot and undershoot, which reflects the finite bandwidth and phase margin of the control loop. This is exactly what we expect from a properly tuned system: stable, well damped, but not artificially ideal. This gives us confidence in the compensator design, but it is still an idealized view. Next, we will see what happens when switching effects are included. This schematic now represents the real switching implementation of the boost converter. Unlike the averaged model, we explicitly include the MOSFET, the diode, the gate driver, and the PWM modulator. The control loop and compensator are exactly the same as before, so any difference in behavior comes purely from the switching implementation. Here we have the pulse width modulator. It converts the compensator output into a duty cycle by comparing it with a ramp signal. This is exactly how real controllers, both analog and digital, generate switching commands. The gate driver introduces realistic non-ideal effects such as propagation delay, finite rise and fall times. These effects are small, but they introduce additional phase lag and slightly reduce performance. And now we have the real power stage. The inductor current is no longer averaged. It ramps up and down every switching cycle, and the MOSFET and diode switch continuously. This introduces switching ripple and makes the system behavior closer to real hardware. Now let's run the simulation. I apply the same load step as before, and we will observe as well the output voltage and the load current. Simulation will take some time, so we will continue when simulation is finished. Okay, now simulation is finished. At first glance, the response looks very similar to the averaged model, and this is an important result. So it means the average model correctly predicts the overall system dynamics. Now, if we zoom our voltage, we can see several differences. There is now visible switching ripple, and the waveform shows small cycle to cycle variations, and the transient deviation is slightly larger. The undershoot and the overshoot are now around 250 millivolts compared to about 200 millivolts in the averaged model. And this is the key insight. The switching model is not fundamentally different, but it is slightly worse. This degradation comes from PWM sampling effects, gate driver delays, switching losses, and inductor current ripple. All of these reduce the effective control bandwidth and phase margin. So what we see here is exactly what happens in real hardware. The averaged model gives an optimistic prediction. The switching model shows the true performance. And this is why both models are important. The average model is ideal for design and fast analysis, and the switching model validates the design under realistic conditions. At this point, we have verified the compensator in two independent ways, and since both models show a stable and well damped response, we can be confident that this design is ready for real hardware implementation. So, what can we take away from this? Designing a boost converter control loop is not just about making it look stable in an averaged model. The averaged model is essential. It gives you a clean and fast way to design your compensator and understand the system dynamics, but it's only the first step. Because once you include real switching effects, you always get slightly worse performance, larger voltage deviations, small additional delays, and reduce effective bandwidth. And this is exactly what we saw in this example. The averaged model predicted a stable and well damped response, and the switching model confirmed it, but also revealed the real limitations of the system. So the correct workflow is always design, then averaged simulation, then switching validation, and then hardware implementation. If you skip the switching model, you are missing a critical step, and that's often where real designs fail. If you want to try this yourself, you can download the exact LTspice models, including both the averaged and switching versions, for free from HK Academy. The link is in the description below. In upcoming videos, I will move to real hardware and show how these simulations translate into practical results. Thank you for watching and see you in the next video.